Alright, so this is your typical neuron found in nervous tissue, and let's break down the basics. So with your typical neuron, you have a few key structures that we're going to point out here. You have the soma, which is just the body right here, and within that soma you have a nucleus, which is right here. On the outsides, you have your dendrites, while going down, you have the axon. But before you have the axon, this structure right here is known as the axon hillock. Like I said before, this long section right here is known as the axon. And down at the end of the neuron here, we have the terminal abrasion, which is this part right here, followed by these knobs known as synaptic knobs. So now focusing on how a stimulus is sent through or travels through a neuron, you'll start up at the dendrites. The dendrites are what receive the stimulus, and when they do that, these receptors on the end of the dendrites that pick up a neurotransmitter called acetylcholine. Acetylcholine is transmitted across the synaptic cleft and picked up by the dendrites, which stimulates a local potential, which I'll get to in a second, inside the soma of the neuron. Now, after that happens, if there's a large enough stimulus from the local potentials, it'll stimulate an action potential, which will travel down the axon and lead to the synaptic knobs at the end, which in turn will release ACH or acetylcholine to the next neuron to continue the stimulus. Now, two things that we're going to go into more in-depth information about are, like I said before, a local potential and an action potential. So for local potentials, let's focus on this area right here. So again, in the soma of the neuron, and for an action potential, we're going to be focusing on the axon right here. What I'm showing here will be a diagram demonstration of a local potential. Again, this is occurring in the soma of the neuron or the cell body before it gets to the axon. A local potential is also what determines if there will be an action potential, which I'll get to next. So starting here, right now we're at what's called resting membrane potential. So right here we have our ICF on this side of the membrane, and up here we have our ECF, intra and extracellular fluid. So within this area, in the ECF, right now at resting membrane potential, it is positively charged, while in the ICF is negatively charged. Not pictured here are some sodium and potassium leaky channels. These would be channels that have a constant influx and outflux of sodium and potassium. So potassium is slowly always going out of the cell, while sodium is slowly always going into the cell. So again, those are not pictured here. So here we have our potassium channel, our ligand sodium channel, and this will be later seen as a sodium-potassium pump. So for a local potential to happen, again, we have acetylcholine, the neurotransmitter, as a stimulus. So acetylcholine, or ACH, has been released by another neuron, and this particle will bind to a ligand, the sodium ligand gated channel, and that will cause this channel to open. Once this channel opens, sodium can now move into the cell. When sodium starts moving into the cell, we have to pay attention to concentration gradients of sodium and potassium on both sides. Sodium is a positively charged ion, or a cation. So as sodium is influxing into the intracellular fluid and out of the extracellular fluid, we now have this charge right here, or the ECF, starts to become slightly more negative, while this charge here starts to become slightly more positive. This whole process is also known as depolarization of the cell, again at the neural soma or the body, because this is a local potential. Now, after this happens, the cell now has to repolarize, and to do this, we now need to account for these concentration gradients here because of the influx of sodium. So now the ICF is a lot more positive than it was at resting membrane potential, and the ECF is a lot more negative. So now what happens is the ACH that was bound to the ligand-gated channel is now broken down and released, causing the sodium channel to close. Now what happens is the potassium-gated channel now opens, and because of the concentration gradient again, potassium can now exit the cell. So moving back towards our concentration gradients, potassium, like sodium, is also a positively charged cation. So we no longer have to worry about the ECF becoming more negative, because now it's just becoming positive, or becoming positive again, due to potassium going out. As well as, since positive charges are leaving, the ICF starts to become negative once again. Now to fully return to resting membrane potential, we have to then bring our attention to the sodium-potassium pump, which will be right here. The reason why we need the sodium-potassium pump is because, remember, when we started, we had sodium on the outside and potassium on the inside, but now it's flipped, where we have sodium on the inside and potassium on the outside. So this is the process of which the cell then, in a sense, pumps sodium back out and pumps potassium back in. And this process requires ATP. So ATP must be present, and this sodium-potassium pump will now pump out sodium and pump in potassium at a rate of 3 sodium for every 2 potassium. And that is the sodium-potassium pump, which restores these concentration gradients back to their same values at resting membrane potential for a local potential. Alright, so now shifting our focus to action potentials, we're going to represent this with a graph. This graph right here represents the level of electrical stimulus in the intracellular fluid of the axon of the neuron. So our y-axis is millivolts, which will be, you could say, the charge given off by the different concentration gradients. In this case, it's dealing with intracellular fluid, as well as our y-axis, which will just be time. And for this, I just won't label it. So let me call a few things to your attention right away. We have two values right here. -70 millivolts will be known again as our resting membrane potential. So for the first part of the graph right here is our resting membrane potential, where the intracellular fluid is at -70 millivolts, where there is no stimulus yet acting on the axon of the neuron to produce an action potential. Now, this value here, -55 millivolts, also seen by this dotted line, is known as the threshold. Now, the threshold is the set value that will cause an action potential to happen. So action potentials are an all or none, which means once it reaches this threshold, it'll go and it'll finish. But this is the key value for that threshold of, again, the intracellular fluid has to reach -55 millivolts for the action potential to happen. Now, looking at this graph, let's pay attention to this area right here. And as you notice, at this point, the graph begins to slowly rise up, indicating that the intracellular fluid is slowly becoming positive, okay? So this area right here is our local potential. So if you recall the last part that we just did, showing how local potential happens with its membrane and the gated channels and etc., this is the local potential represented on the graph. So this is the stimulus that leads to an action potential, okay? So if this local potential reaches the -55 millivolts right here, then this action potential will be sent down the neuron. So let's say, going along with this graph, the local potential happens, stimulus reaches -55 millivolts, then an action potential can happen. Okay, so we've already discussed this process down here. Now let's focus on what's going on up here. This area where it spikes up at the beginning of the action potential is known as depolarization. What happens in depolarization is, well, you can take a guess just based on how this graph is working. If the intercellular fluid is becoming increasingly more positive, then you will have sodium rushing into the cell or the neuron, into the neuron at a very high rate, very quickly. Now, one way an action potential differs from a local potential is that this influx of sodium at this point deals with voltage-gated channels, which respond to the threshold. So instead of responding to a ligand or ACH binding to the top of the channel and opening, these channels respond to the stimulus of electrical gradients of the intracellular fluid. So we have sodium influxing, rushing into the cell, ICF becomes increasingly positive. On the other side, when we're going back down, this is known as repolarization, where we have potassium leaving the cell at a very quick rate as well. So that means the intracellular fluid that had that potassium and now has sodium is kicking all that potassium out to lower the value and allow the ICF to become negative once again, which is seen on this curve, this portion of the curve getting increasingly negative. Now, if you notice at the very bottom, if we were to draw a line a dotted line for the resting membrane potential right here. Now you notice how after repolarization it dips far below the resting potential value. So now the intracellular fluid is now below -70 millivolts. Okay, so this is called hyperpolarization, and this has to deal with a process called refractory periods. Now, in refractory periods, basically what it means is a time that the neuron cannot fire, and there are two types of them. We have absolute refractory periods and relative refractory periods. So the absolute refractory period would be from the original stimulus of the local potential to the dip of repolarization. That would be the absolute refractory period. Now the relative refractory period would be from the portion where the curve dips under the resting membrane potential to when it reaches resting membrane potential again. That would be from here to the end, and this is known as relative. Now with absolute refractory period, there can be no more stimulus, or another action potential cannot be sent. This is a time where no matter how strong the stimulus is, it's kind of like a resting time for the neuron where nothing can be sent because it's too busy already sending them. Now, the relative refractory period down here is just a way of saying that the cell is trying to reach resting membrane potential again to be ready to fire again. However, if a stimulus is strong enough, a neuron can start another action potential from or during this relative refractory period. It just takes a stronger stimulus because, again, the voltage-gated sodium channels are relying on these values on the side. So if it reaches that threshold of -55 millivolts in the intracellular fluid, then it can send another action potential. So let me get back to hyperpolarization real quick and then we'll be done. Hyperpolarization deals when too much sodium is kicked out of the cell to a point where the intracellular fluid is far below -70 millivolts. Because again, if potassium is a positive ion and it's leaving, then that means the ICF is going to become more negative. And when that happens, the neuron will tend to overshoot that and have to reach its resting membrane potential again through this graph. Maybe this curve may show this to be a little bit more drastic than it actually is. This hyperpolarization, in fact, does not actually become that negative. It's more like just a little kind of jump underneath, and then it will head back. So again, those leaky channels can restore that resting membrane potential fairly quickly, because this is probably within about a 5 millivolt range. Alright, so that is the graphical representation of an action potential